You've been hearing a lot about vectors in the industry, but how does this relate to Azure SQL Database, and how quickly can you get started? Learn all about it this week on Data Exposed. Hi, I'm Anna Hoffman, and welcome to this episode of Data Exposed. Today, I'm joined by Davide Mauri. Davide, thanks for joining us.
Hey, Anna. Nice to be here again. Thanks.
It's great to have you here again. And today we're talking about something we've never talked about on the show before, and that is clustering in Azure SQL Database. So before we get into it, I just got to ask you, Davide, you're working a lot in the AI and developer space. What's going on in Azure SQL Database with regards to AI lately?
Well, as you know very well, a lot. So, aside from Copilot I saw you just had a episode with Joe, we are also working on vector support. So soon we'll have, and we actually already announced it in a kind of a sneak peek, native vector support. So we are working to make sure that vector is a first-class citizen in Azure SQL, in SQL Server, of course, and in general going, along that path where we are trying to make sure that creating AI solution in Azure SQL is the frictionless possible experience that you may have with any database. So that's what we are working on right now.
Awesome, cool, thanks so much. And I think the link is aka.ms/SQL AI, so we'll put that in the description.
Oh, that's right.
As well. Awesome, cool. Okay, so then on to some exciting things for today. What did you want to talk about today and show us?
Well, I guess vectors and how you can actually use vectors today in Azure SQL and SQL Server, even if we don't have yet kind of a native vector support. And the reason is very simple, and I really want to stress how important it is for developers to have this kind of lateral thinking. Don't wait for a feature to be there in the product, because as a developer, you are empowered. You have the power to actually create the feature yourself, right? And that's exactly what I did, because we had a customer asking, how can I do vector search today in SQL or SQL Server? And it's actually pretty easy, because at the end of the day, a vector is nothing more than a set of number, a ordered set of number. And we all know that relational databases are great at dealing with set of data, right? So I wrote, I think almost 1 year ago, this article that you can find on devlogs.microsoft.com that shows how you can actually store vector in Azure SQL already. And I will not go into detail here, but basically the point is that you just store each dimension of each vector in its own row, and then you use column store index to speed up search and basically operation on the vectors. And thanks to something called SP invoke external REST endpoint, you can take any object, any idea, any topic that you have in your database. Let's say in this case, I was making the example of the Foundation series by Isaac Asimov, one of my favorite authors, and a very well-known science fiction series. And we need, of course, in order to do vector search, to first of all, turn it into a vector. And you can use SP invoke external REST endpoint to turn that idea into a vector using OpenAI. It's very easy. At the end of the day, you just do something like a SP invoke external REST endpoint, then you call your OpenAI deployment and pass in this case, I was just passing Isaac Asimov as the idea, the object, the topic that you want to turn into vector, and then you save it into your column store. But building on that, of course, the next question that typically developer ask me is, okay, how do I index that? Because if I need to find what is the most similar topic to, let's say, a science fiction author, well, I need to scan all the vectors that has been generated for me, find those who are the closest to this idea. And again, that's exactly what cosine similarity is doing. And then return all the vectors that are somehow similar. Just again, very high level cosine similarity measure the distance between two vectors. If we say that each vector represents something in real world, let's say cat and a dog, right? So V1 represents a cat and V2 represents a dog. Then you can measure how close or how distant they are by calculating this value called cosine distance. Of course, the closer, the more similar they are. The more distance they are, the more different they represent in terms of idea that they underline. So, for example, here I would say dog and pizza would probably be somehow different, right? Definitely less similar than a cat and a dog, even if though cat and dog are not exactly the same thing. So we can do everything that I just said in pure SQL, and it's, again, pretty fast thanks to column store support. And column store support internally use vectors, actually, even in a different way than this one, to speed up CPU calculation. But still, if the only way to exactly find what are the most similar vectors to a given vector is scanning all the table, all the vectors that you have. And as you understand, if you have a million of vectors, this can be time-consuming, resource-consuming, which is not something you want to do on an operational database, because an operational database also has to run the regular queries, right? So how do you reduce the number of resource used while keeping a good answer coming in from your search? Well, one way to do that is using indexes, which unfortunately, even if the word is the same, the concept is completely different than regular index we are used to deal with in a relational database. So we are not talking about B-trees or hash index or any other stuff. Typically, we are talking about actually clustering data. And one good example is something called KMeans cluster, which basically says, let's say that I have all the vectors that I have in my database. And in my sample, I'm using a subset of the Wikipedia articles. So I have 25,000 articles from Wikipedia, all already transformed to vectors, thanks to AI. And let's say I want to find what are the most similar authors to Isaac Asimov. Since I like science fiction, if I like Isaac Asimov, I probably love other books written by similar authors, right? So let's say that I take all the vectors that I have, and let's say there is a way, and this way is actually a K-mean cluster in this case, that automatically groups all the vectors that are similar into one group. So let's say that the pink group that you see here contains all the authors that write some books. And the red groups here are all authors that write some cooking books. Of course, they are similar because they are authors, but yet different, right? So instead of when I search for Isaac Asimov and what are the most similar author to him, what I could do is try to find what is the group that is about author, so it's similar to the concept I'm trying to find, and completely skip those groups. Let's say it is gray one that talks about, let's say, computers, right? So it's probably there is nothing probably interesting for me here, because the concept that these groups underlines, it's very different from the author's concept that I'm looking for. So by having a way to cluster data together and then kind of identify each group with this group is close to this idea, this other group is close to that idea, then we can immediately say, okay, I will just start my search from this group, the pink one, and then extend it to the red one, and then to the Azure one, because since they are close, they are probably similar to some level. That way I can avoid to completely search data in here in the gray group, which allows me to spare a lot of resources. Now, this technique of grouping vectors together is a purely mathematical technique. It's called K-means, and can be done quite easily using, for example, Scikit-Learn. Now, why I don't think it's a great idea on average, then there are, of course, use cases where this is not true. But for a OLTP database, doing this calculating the K-means, it's usually very resource intensive, right? I was telling you before that I ran this on my machine, and with 8 cores, it used it for a minute. All my 8 cores, which is not something I want to happen in a production database, because otherwise it will not have time to answer the queries that my user are running, right? So what I found very interesting is that we could spin up a compute node, run K-means inside that compute node, and then basically move all the data that I have in my database, all the embeddings that I have, into that compute node as fast as we can, do the K-means calculation there, and then save the result, which is called IVF, to be more specific, but it's just an index. Basically, we can save the result into SQL, and then once the results are saved into SQL, we can query the results without having to have that container running. So that container is really used only for the time that we build the clusters. And then we can do everything in SQL. So the search into the cluster, it's cheap and can be done purely in T-SQL. So that allows us to have an index, again, in quote, so a cluster, a K-means cluster that we can act upon as an index and use it to speed up the search. The repository here, Azure SQL DB Vector K-means, is an example of how that can be done. And it's very nicely wrapped into a dev container. So if you download it on your machine, it will take care of even installing SQL Server for you, giving you an example database so you can easily run the example on the Wikipedia data. And let me show it to you. But before that, I covered a lot of stuff. I don't know if you have any question or you just want to see it in action.
I mean, I absolutely want to see it in action, but we'll let the suspense build just a second longer so I can ask. Like this scenario, it seems like it'd be super relevant to a lot of different use cases. Like the one that came to mind was like an e-commerce site and you wanted to recommend her.
That's right.
You would just do this. And then instead of having to like always push out and do the math, what I'm understanding is with this vector index, I can search much more quickly and use it in my application. Is that kind of how it would work?
That's right. And so let me show you. Here I started a container that I created that contains SciKit-Learn, the famous Python package that allows me to quickly do a K-means cluster in the most efficient way. And I exposed the SciKit-Learn K-means feature as a REST endpoint. And again, it's very easy to call a REST endpoint from any language. So here, just to simulate what is happening behind the scene, I have this simple UI that allows me to say, hey, what is my server status? Let me just, perfect, nothing is doing. This is my container running K-means. So it's doing nothing, perfect. That's exactly what I'm expecting right now. So what I can do, I expose the K-means cluster as a REST endpoint so I can ask, hey, please build the index for me. This is the table I want you to target. This is the vector. This is the column that contains the vector. And this is the ID of the vector. So I can then join back the result with my original table and get not a vector, but a title, for example, or a name. And this is just information about how many dimensions my vector have. So let's run this, and you will see behind the scene that this has started creating the index. So now what is happening is that my container is pulling data from SQL Server in my case, because everything is running locally, but this can be easily deployed in the cloud, and is moving all the data in the container. And here SQL is doing pretty much nothing. It's just pulling data out as it very well suited to do. So the container is now starting to load the data. It should take just another bunch of seconds. Now it's creating the K-means model. Now my container is using as much as CPU as they can. But again, my database is untouched by this resource usage. And by default, given the amount of numbers, we automatically determine, the sample automatically determines how many clusters you need on average. So 50 clusters should be enough to allow you to quickly find what you need. And then once it will be done, and as you see, it's taking a while, even if it's not that much data, it will save everything into SQL, and it will even create a wrapper function for you. So you don't have to worry about how to actually run the query. You just use the function that is created and you're done. So that should happen anytime now. And then after that, it will create the function. But I already did it. So let me go here. And this is basically the function you will end getting. So find similar vectors on the table and the column that you have indexed. And then you can specify the vector you want to search for, how many cluster to scan. This is also called a cell probe methods, because basically you define how many cluster do you want to touch. If I'm touching 50 cluster, I'm scanning all the data here. So this will be what we call the exact result, because we are not leaving out any vector, right? Of course, we will pay for that in terms of resource usage, but we are scanning everything. In the meantime, let's see if this is done. Not yet, so hopefully it will. Okay, now it's done saving some data into SQL, and fantastic, my index is created. So I can now run this query, and I'm trying to find what are the authors that are similar to Isaac Asimov. I would expect to find Isaac Asimov as the first result because, of course, Isaac Asimov is similar to itself, and then some others, right? So let's take a look, and let's just re-execute to make sure the cache is warm. And it took 1 second elapsed of 5 seconds of overall CPU usage, because again, for each vector, we have to calculate the distance between our vector and the reference vector, which is in this case Isaac Asimov. And to do that, we have to calculate the distance taking into account 1536 dimension. So there's a lot of multiplication and math going on here. That's why the CPU is kind of quite heavily used. Now, the result is Isaac Asimov, of course, then Heinlein, Carl Sagan, and if you are into science fiction, you would recognize this name. Now, let's say that I only want to scan 4 clusters, not 50, which is 1/10 of the original, right? So let's see how fast it is and if the results are still good. Yeah, they are still pretty good, right? Because the first 4 are still the same, but I got the answer only in 300 milliseconds overall and 1 second CPU. So it's definitely 5 times less expensive. So this is the proof that right now, I'm actually searching across the clusters in purely T-SQL, reducing by, in this case, time 5, the resource usage, and still getting exactly the results I want. So this is on 25,000 vectors. Imagine having it on 1 million. You can save a lot of resources and still have the results that you want, right? All in SQL, and just offloading the compute part to a container so it will not affect the performance of your database. That's
awesome. Yeah, this is super cool, Davide, and I'm going to go try this out myself because it's also easy to get my hands on. As we wrap up, I know there are other KMeans methods or similar methods that people use. Will SQL work with those?
Yeah, so basically any clustering method will work. Actually, K-means can be calculated in with different techniques. So you can just explore the one that fits better your data. At the moment, it's very trial and error in the sense it depending on your data, one way of cluster may be better than the other, but it's easy to explore. Then there are even other, maybe we can do another episode in future. There are even other techniques where you can even offload the querying to a more specialized library like FICE, so that you don't even have to search in SQL. You can just use sp-evoke external REST endpoint to call the REST endpoint based on FICE. So even the search is completely, let's say, outsourced. And depending on where you land in terms of kind of balance between having everything in SQL for security and performance or offloading a bit to an external container, either one of the two can be the best one for you. So it's up to you to choose. Definitely, I'm also working on integrating files in SQL, but that's a little bit more complicated, but definitely K-means is a great way to start, even to understand how all this vector word works, right? Because I guess vector today is the new common word. With AI, everyone needs to be a little bit, I would say, confident in handling vector. So that's a great way to start and also to build something useful.
Cool. Awesome. Well, Davide, thanks so much for coming on the show. I learned a lot. I'm sure our viewers did too. If you watch this episode, go try out this sample. It's available. We'll put a link in the description for you to learn more, and maybe some blogs that come up related to this or FICE as time goes on. So be sure to come back here, like this episode, and we hope to see you next time on Data Exposed.